Between land and sea lies a seemingly barren strip of sand. But it's an extraordinary place, one of the richest habitats on Earth, where life continually struggles against the elements. In a moment, we'll see how various creatures manage to survive the relentless changes of the intertidal zone. Peter Parks, a zoologist from Oxford University, knows this Cornish coast well. For years, he's been coming here with his wife, Susie, to observe the teeming forms of life between the tides. Cornwall on England's southwest coast is an ideal study area because of the tidal extremes, up to 20 feet between high and low waters. As the tide falls, large areas of shoreline are exposed, creating a dramatic change in the state of the habitat. Most forms of life have to cope only with seasonal changes a few times a year. Here, with the tide moving in and out day after day, life must cope with changes every 6 hours. And these changes can be violent. Pounding waves can turn the seashore into one of the most demanding environments on Earth. It seems an inhospitable place, yet many forms of life have adapted to withstand the rigors and dangers, the action of tides and waves, land and sea predators, stranding and dehydration. Because the rocky shores are full of troughs and hollows, pools remain as the tide recedes. Although some are many feet above the high tide line, they are replenished by spray from breaking waves. The animals and plants that haunt these pools live a double life. Submerged by several feet of water at high tide, many live for hours out of water at low. All these shoreline species face dangers which somehow they have been able to overcome. How they manage to do it is the particular study of Susie and Peter Parks. What enables this crab to live in the rock pool? Can it get away when the pool dries out? And if it does escape, how can it breathe on land? What will happen to the butterfish when the pool dries out? To help answer these questions, Peter and Susie rely on sophisticated photographic tools, for the world of life between the tides is largely invisible to the naked eye. Among a group of young scientists at Oxford who specialize in biological films, the Parks often build their own precision equipment, such as this periscope attachment that's designed for the shallow water of rock pools. It works like a submarine periscope in reverse, enabling a person to look down instead of up. Mounted on top of the periscope, the camera photographs an image reflected by a mirror below water to a mirror above. The whole apparatus can be turned so that the movement of animals underwater can be followed. The periscope reveals a great richness of life. But rock pools also contain an entire world too small to be seen with a periscope. Microscopic animals are taken back to Oxford, where special equipment brings them into man's field of vision through photomicrography. Millions of years ago, sun and sea came together in a powerful mix. Life. Microscopic plants were the first living things. And they made it possible for higher forms to evolve. For each green plant changes sunlight into food and gives off oxygen. More than half of all the oxygen in our atmosphere is produced by these microscopic drifters, phytoplankton, our lifeline between sun and earth. With abundant light and oxygen, the coastal waters are nurseries not only for plants, but also for the swarm of tiny creatures that turn the sea into a living broth. Stirred by currents, cast-off shells of tiny crustaceans, such as barnacles, are continually added to the nutritious brew. We can even watch a barnacle shedding its skin. In the ocean's food chain, nothing is wasted. The dead become food for the living, planktonic forms of animals recognizable only under a microscope. These shimmering larvae, the first stages of sea creatures, are perfectly formed animals and can feed themselves, sometimes with a vacuum cleaner type action, sucking in plankton smaller than they are. Millions of them are wafted by the currents, but only a few will survive to adulthood. Most will meet a violent end inside the stomach of a larger animal. Each incoming tide, carrying its wealth of microscopic plants and animals, brings a supply of fresh food. But the only creatures that can take advantage of this rich banquet are those that have been able to adapt to the ebb and flow of the tide with its pounding waves. The limpet withstands the waves by clamping down tightly on a rock when it feels a wave coming. Such an adaptation has enabled this species to survive for millions of years. Investigating this tough little creature, Susie Parks finds that its shell acts as a protective armor against predators. Clinging to a rock doesn't require complicated sense organs. The limpet's survival depends mainly on a powerful ring-shaped muscular foot with which it holds on, becoming almost inseparable from its habitat. Underwater, photomicrography reveals that it feeds only during high tide, grazing on the thin film of algae found on the rock face. After feeding, it always returns to exactly the same spot where it has grown to fit the contours of the rock. Mussels, too, must keep a strong footing to avoid being swept out of their bed. A remarkable appendage, the foot of a mussel can distinguish between light and dark, which helps it to find a suitable place in a dim crevice. Then the foot secretes a fluid which hardens on contact with water. Thin nylon-like threads are formed with sticky ends that anchor the mussel to the bottom. For every intertidal creature, keeping a strong footing is crucial to surviving the turbulent conditions. The starfish doesn't have to rely on just 2 feet, or even 3 or 4. In a remarkable view, we can see it's equipped with an entire army of feet, each with its own suction cup. The purple-tipped sea urchin also has a vast number of sucking feet. Situated between its spines, they enable each part of the body to clamp itself to a rock, even a vertical face. Tiny muscles in the tip of each foot create a vacuum which cause the sucking action. Normally, this action would be invisible. Here, it's magnified hundreds of times. Plants, too, must withstand the sway of the sea. Unlike land plants, they are infinitely flexible and to some extent elastic, adapted to the motion of the tides. Without soil in which to put down roots, tide-line plants like kelp have a unique root-like organ, a holdfast. Made of the same material as the stalk, it anchors the plant to a stone. Tide-line plants and animals live side by side in intimate and sometimes surprising associations. This seaweed, for example, provides a habitat for tiny organisms. Under a laboratory microscope, they can easily be mistaken for plant cells. But a microscopic view of the same surface underwater reveals bryozoa, tiny animals just 1/64th of an inch long. By the millions, they colonize seaweed in self-built hives, yet each animal is quite independent. Beautifully designed for their niche and tidal life, bryozoa compartments have spines which prevent them from being knocked off the seaweed into the swirling water. In spite of their adaptations to such punishing conditions, ebb tide is particularly dangerous for animals that cannot survive out of water. Some manage to swim out with the tide. Some don't. Death to some means quick and easy food for others. The shorebirds can't rely on this kind of bonus, and at low tide, some of them spend all their time searching for living animals. Some tide-line animals survive by hiding in the sand. Digging for lugworms, fishermen often come across one of these spiky balls, a burrowing sea urchin or sea potato that lives 4 to 8 inches under the moist sand. A forest of spine-like organs enables it to breathe and plow along under the sand. The tiny creatures on which it feeds are collected with flexible tube feet that often become clogged with debris. These tiny pincers may be the means of keeping the feet clean and of getting rid of parasites. Exposed, the urchin would not last long. If it is unearthed, it quickly digs in again where it will be secure, unaffected by the changing tides. For the small shore crab, the sand is also a refuge against the danger of dehydration at low tide. The larger, more powerful edible crab looks tough enough to survive all dangers, even low tide. But when stranded, there are chinks in its armor which make it vulnerable to the sharp beaks of birds. Yet Peter and Susie Parks have found that for short trips out of the water, the crab is well equipped. Positioned over its gill openings, bubbles of air keep the gills moist, enabling the crab to breathe on land. To survive a short overland journey, the crab relies also on its extraordinary eyes, which can turn in almost a complete circle. The eyes must be wet in order for the crab to see, and they're equipped with a built-in eye wash. Mounted on a kind of cup, each eye is constantly rinsed with water from within the crab's body. With these aids, the crab can scuttle to a deeper and safer pool. On warm, windless days during low tides, when no spray finds its way into a pool, the oxygen content begins to drop. But some fish can cope even with this problem. Like all fishes, the blenny breathes through its gills, extracting oxygen from the water. But when oxygen is scarce and the blenny's gills cannot extract enough, the fish can breathe through its fins as well. The fin membranes are so fine that the blood can absorb oxygen directly from the water, making its entire body surface, which has no scales, one giant breathing membrane. In this way, the blenny survives. Apart from dehydration and lack of oxygen, animals of the tidal pools face increased danger from predation at low tide. For these creatures, nature has provided a remarkable adaptation: camouflage. One of the most unique rock pool residents is a little crustacean, the sea slater. Almost invisible against a rock, it could easily escape a predator's eyes. Like the blenny, it too can survive in water with little oxygen, since it has movable gills under its tail. Equally well adapted to land, it can exist where the ground is merely damp, a creature of both land and sea. For most intertidal animals, low water conditions last only between 6 and 12 hours. When the tide returns, it brings more oxygen, more food, and also an opportunity to reproduce. Rock-bound, barnacles can't move about to mate. They rely on the sea to carry their sperm to other barnacles. At high tide, millions of sperm are released into the water. Some penetrate other barnacles, fertilizing eggs which develop into larvae that are pushed by the millions into the sea. Like most other marine animals, barnacles begin life as zooplankton, perfectly formed microscopic animals. In all, there are 8 stages of development, each of which must survive the dangers of predation before the final stage can attach itself to a rock and mature. Very few larvae reach adulthood. Most are eaten, but enough survive to carry on this ancient species. Mixed and whirled by the waves, millions of larvae of hundreds of shore species populate a microscopic universe. Most bear no resemblance to their final form. The limpet starts off like this. Some, such as the sea snail, seem to have better chances of survival than others. Its larva has a protective casing. With the help of hundreds of tiny oars, or cilia, it moves along. Although the top is less than 1/32 of 1 inch wide, we can see its heart beating. The structure of the edible crab is already discernible in its first larval stage. Here, the large eye can be seen, and the first traces of the adult red coloration. In a further stage of its metamorphosis, it has to gain a foothold on the ground in order to become a crab as we know it. But it's still as small as a pinhead, and its heart much smaller than a pinpoint. All these tideline creatures produce larvae which are strangely beautiful. This is how a sea urchin starts life. pouring their eggs and sperm into the sea, starfish produce these. The sea potato reproduces in the same sort of way. Its larvae may drift for miles to other sandy shores. Even the tiny plant colonists, the bryozoa, continue to establish new communities with their swimming larvae. And so all the slow-moving creatures of the shore spread to other parts of the intertidal zone, passengers of the tides. The chances of each larva arriving at its adult form are only 1 in hundreds of thousands. For in their planktonic form, the animals become part of the numerous food chains of the sea. However great the dangers, enough larvae survive the jellyfish and the many other predators to populate the tidal zone with an enormous variety of species. In its own way, each has solved the problem of living with the constantly changing extremes of high water and low, the turbulence of the sea and the drying heat of the sun. It is a world betwixt and between earth and water, a fertile world of microscopic proportions, yet of global importance. For out of these elements, the powerful chemistry of life began, and on them it still depends.